Hello, this is Mr. Mac. This is a concept video on some of the applications for exponential and logarithmic functions. Now, to start off with, many things can be modeled by exponential functions. There is a basic exponential function that deals with growth, and that will be of the form f of x is equal to a times e to the kt. Now, the exponential function that models decay is f of x is equal to a times e to the negative kt. Now, basically, the difference is the sign of the exponent. Remember, if the exponent was positive with a number greater than 1, the graph looked something like this. In other words, as time goes to the right, it goes up. And if the exponent is negative, the exponential function looks something like this, and it would asymptote towards the x-axis. So basically, a lot of times what you have to do, if you've got something that's either growing or decaying, you have to ask yourself, is this a situation where as time goes by there's going to be more, or as time goes by there's going to be less? And that's one way to decide whether we're talking about a growth or decay situation. Now I'm going to just group these together and minimize them so that they're not in the way. Now let's take a look at a couple of examples. First of all, one example of exponential decay is radioactive decay. And maybe a word or two about Halflife. If you have a radioactive substance, as time goes by, this molecules of this substance will give off particles and become another element that's fairly close to it, or something like that, chemically speaking. And this is called radioactive decay. And the way we ordinarily talk about how fast this happens is we talk about an element's half-life. The one that I happen to have here is carbon-14. I happen to know some information about carbon-14. So let's talk about carbon-14. Now, the half-life of carbon-14 is approximately 5,730 years. What that means is, let's imagine that we have 16 grams of carbon-14. Now, if we wait 5,730 years, that original 16 grams, only 8 grams of it will still be carbon-14. Now, there will probably be some other substance, maybe non-radioactive carbon or something, mixed in with this substance after the 5,730 years, but only 8 grams of the carbon-14 will be radioactive carbon-14 after 5,730 years. Now, after 11,460 years, now, if you do the math, that's 2 times 5,730 years, there will be 4 grams of carbon-14 left. Now, in another 5,730 years, what would that be? 0, 9, 1, 7, 1. In 17,190 years, there would only be 2 grams of carbon-14 left, and it would continue on like this. So theoretically, we would never get no carbon-14, but the amount of carbon-14 is cut in half each time it goes through a half-life. That's why we call it the half-life. Now, if, and you all have probably heard that scientists will use carbon-14 to date, I cut that off. We'll use carbon-14 to date fossils and so forth. And the idea is something like this. There is a relatively constant amount of carbon-14 in our environment around us. And so scientists know what the amount of carbon-14 is in a live individual. So as I breathe and eat and give off water and all that kind of stuff and everything, I keep the amount of carbon-14 in my body at a relatively constant proportion, which is very similar to the amount in the environment around me. But now, when an organism dies, it stops respirating, it stops breathing in, it stops giving off things and so forth. It's there and it begins to decay, but the material just kind of stays there and stuff doesn't go in and out anymore. So at that particular point, the amount of carbon-14 that organism had in it when it died is fixed. And so if you measure the total weight of the organism and you measure the proportion of carbon-14 in it, you can figure from that approximately how long it has been since the living organism died. So carbon-14 can be used pretty easily to find out how old something is. So now, let's take a look first of all at the equation. F of x is equal to a times e to the negative kt. Now, or f of t here, let's do that, f of t. Now, what we would like to do is we would like to find what k is in this particular case. Now, a is always going to be the initial amount, and then f of t is going to be the amount after t years. Now, if we use 1 for a, what we're doing really is we're saying 100%. Then the decimal that we get over here would be a percent of that carbon-14 that remains. And a lot of times that's what they'll do. They'll say there's 14% of the carbon-14 that would be in a live organism, or 37% of the carbon-14 remains, or something like that. So what you would do is you'd put 0.37 in this particular spot right here, and we would actually just have a 1 in the A spot. And that makes it pretty easy to figure these things out. So now, what we know is that F of 5,730 is going to be 50% if it's carbon-14, because remember, carbon-14's half-life is 5,730 years. So after 5,730 years, 50% of the carbon-14 will remain. So we could solve for this k right here by saying 0.5 is equal to e, and remember a is 1, e to the negative k times 5,730. Because the time is 5,730. Now all we need to do is to find the value of k. Okay, first of all, rewrite this a little bit. 0.5 equals negative 5, 0.5 equals e raised to the negative 5730k. Now, this is an exponential equation, and the variable, the unknown, is part of the exponent. So one of the ways that we can solve this is by rewriting this in exponential form. Now, the cool thing is we've got a base of e, and we have a logarithm that has a base of e on our calculator, so we can just use the natural logarithm. In other words, this rewrites as log base e of 0.5 is equal to negative 5730k. That's an equal sign there. There we go. Now, to solve for k, we would simply divide both sides by negative 5730. Now, let's get the calculator and actually do this calculation. Clear what we got there. So log base E, that's the button right next to the 4. So, and notice it says ln, we think of that as natural log, 0.5, close parentheses. Now we're going to divide that by negative 5730, and we get this number. Now, look at the, over there at the end, we have 1.20968, etc. E negative 4. Now that's scientific calculator speak for scientific notation, which means times 10 to the negative 4. Now, these exponential functions are extremely sensitive to variations in this exponent. So my recommendation is that instead of writing down part of this constant and just typing in each time, let's put this in the K register in the calculator. So while this is the last thing that's happened, you press stow, that's the button right to the left, immediately to the left of the 1, and you get and's arrow, and then press alpha and then K. Now I believe K is the left-hand parentheses. Now if I press enter, you're going to see the number again, but what that did was that put that in the K register. So now anytime I need that constant, boom, it's there. Now the question is, okay, we can ask several questions. Okay, how much, or what, let's change this. What percentage of the original carbon-14 would remain in a fossil after 10,000 years? Well, what we would do is we would want to find f of 10,000 where the original amount A is 1 e to the negative kt. Now, oh, yeah. Now, k was, let's see what it was. What was it? 1.209, 1.21, negative 1.21 t. Now, notice I'm not going to type in negative 1.21 t. T is actually 10,000 here. Okay, I'm not going to type in negative 1.21. What I'm going to type in is negative k. Now, there's something really nice in the calculator. The second function on the natural log function, the button to the left of the 4, if you press second and then natural log, you get e raised to it. It's already ready for you. Now, what I'm going to put here is alpha, oh, excuse me. I need to put a negative sign, and then alpha k times 10,000 and close parentheses. Now, when I press enter, I get 0.29829. So approximately 29.9% of the carbon-14 will remain after 10,000 years. Now, notice, because of this, if I were to change this around and say, fossils is examined and found, and it is found that 29.9% of the original carbon-14 remains, how old is this fossil? And we would work back the other way, and hopefully we would find 10,000 years. Let's do one of those as well, okay? So what we're looking at right now is let's pick a value. Let's say we've examined a fossil. Fossil is examined. Is it IL or EL? I don't really remember. Am I misspelling fossil? I don't know. Maybe I'm misspelling. No, fossil. There it is. Fossil. That's right. Okay. Fossil contains 42.7% of its original C14. How old is the fossil? Okay. So what we do now is we put 0.427 equals e to the negative 1.21 times 10 to the negative 4 times t. And now we need to solve for this t. Once again, the easiest way to do this is to rewrite this exponential function in logarithmic form. So we have the natural log base e of 0.427 is equal to negative 1.21, etc., times 10 to the negative 4 times t. We want to solve for t, so we divide both sides by negative 1.21 times 10 to the negative 4. Okay. Now, we'll cross this out. And so what we have is t is equal to this value. Now, we can do that on the calculator. And since we haven't messed with the constant, we still have negative 1.21 times 10 to the negative, well, actually, we have 1.21, etc., times 10 to the negative 4. So all I need to do to find t is I press natural log and 0.427, close parentheses, divide. Now, I'm going to have to type negative k because I need that negative sign. It's not in the constant already. And get rid of that. Okay, there we go. And so when I press this, we say 7,034.67. So about 7,030 years. It doesn't make much sense to go more digits of significance than you have in your original question. If you say it's 42.7%, then it's 7,030 years is probably as close as you should report it. Okay, so that takes care of an example of radioactive decay. For each different type of radioactivity, there is a different constant. But the constant for example, carbon-14 is the same anytime you're dealing with carbon-14. The constant for uranium or plutonium or cesium or one of those others is a different half-life, so there would be a different constant in this radioactive decay formula. Now let's go to exponential growth. Now exponential growth includes things like investments and population growth. Populations grow exponentially. And so we've got f of t is equal to a times e to the kt for population growth. Now, ordinarily what we're going to do with population growth is we're going to have some base year that we're going to zero t out as. For example, we'll use Smulgaria because I don't know Smulgaria. Had 7,862 people in 1989. And so let's say that population had grown to 10,541 people in the year 2000. So question one, what is the function for the population of Smolgaria, where T represents the number of years since 1989, and number two, how many people live in Smolgaria now, or something like that. Now, I'm going to pause this and come back to it in a little while. Hi, I'm back. Now, the first question that we're asking about Smolgaria is, what is the population function? And then I'm going to put here in parentheses for years since 1989. In other words, 1989, our time, T, is going to be 0, because there have been 0 years that have occurred since 1989 in 1989. And then question 2, obviously, how many Smolgarians are there now? Now, let me just stop here also. I have discovered that there are people who have subscribed to my channel and they watch these videos even though they're not in my class. And if you're not in my class, you probably won't know what Smolgarians are. The Smolgaria is a mythical land that I invented that is populated with incredibly stupid people. And so I like to tell jokes about stupid people, but I don't think it's fair to talk about an ethnic group or people that have a certain color hair or other things like that. So in other words, any of the jokes about stupid people, I just talk about Smolgarians because they are all stupid. And a couple of examples. Smolgarian scientists have invented wonderful things like dehydrated water, the solar-powered flashlight, and the ejector seat in the helicopter. That's my personal favorite. Their scientists were going to send 2 astronauts to the sun. Somebody pointed out it was extremely hot on the surface of the sun, to which the Smolgarian scientists said, that's okay, we're going at night. Anyway, so that's Smolgarians. Now, getting back to work here. So first of all, what we have to do is we know that in this function, A is going to be equal to the population in 1989. So A is going to be 7,862. But what we have to find is the K. So let's see if I can get full screen here. Is this working any better? So yeah, okay, now I've got some room here. So what I've got is f of, okay, now for the year 2000, T is going to be 11. That's 2000 minus 1989. So 10,541 is equal to 7,862 times E to the K T, but T is 11. So we need to solve for K. Now, first, actually I need my calculator here, so let's see if I can get the calculator up on the screen. And then go back to full screen. There we go. Now, having a little trouble here. Oh, okay, I guess that's it. First, I'm going to divide 10,541 by 7862. Now that gives me 1.34, etc., is equal to e to the 11k. Now, I'm going to actually use all of this number. I just wrote a little bit of it down on the board here, but I'm going to actually chain my calculations. Now, what I'm going to do is I'm going to change this exponential equation to its logarithmic form. So the log base e, that's natural log, of 1.34, etc., is equal to the exponent, which is 11k. So k is going to be the natural log of 1.34, etc., divided by 11. Now, that's pretty easy to do because I have that number right in here. So I can just say natural log of the answer that I have sitting there, close paren, divide 11. Now, this number is going to be the constant for the Smulgarian population. So I'm going to store this in the K register. Okay, so natural log of the answer divided by 11, store K, there we go, 0.026657, etc. So K is approximately equal to 0.0267. And so if I write that, that's fine, but actually what I'm going to use if I do any computing is I'm going to use K in the calculator. So the second question was, how many Smulgarians are there now? So 2015 minus 1989 is 26. So now, oh, first of all, I didn't really write the equation, did I? So let's write the equation. What is the population equation? I'll just put it right here. It's P of T, population, is equal to 7862 times E to the 0.0267T. Now, how many Smulgarians are there now? We're going to put 26 in for T. So we have 7862 e to the 26k, close paren. There are 15,723 Smulgarians, very stupid people. Actually, it seems to me like there's a lot more than that. But anyway, only 15,700 of them so are Smulgarians. All right. Now, you can use those concepts for population. The exponential function for population. Now, there's another type of exponential function that they want to introduce, and this is the logistic growth function. Now, see, populations grow exponentially, but then at some point, many times, there's some limiting factor. If you think about the world's population and the people, if we continue to grow exponentially, there will come a time when we would all be standing on the surface of the globe, shoulder to shoulder, without any room to move. But long before that, we would be taking up so much room that there wouldn't be any room for food to grow and other things like that. So in other words, there are limits to the number of people the world can actually handle. Now, the exponential function looks something like this, and after a while it just takes off to the right. Now, the logistic function has a similar look. Early on, it looks something like this, but then what happens is after a while, it begins to level off because of limiting factors. Now, the logistic function is f of t is equal to C over 1 plus A times e to the negative bt. Now, C and A and B will be values, at least for Algebra 2 students, that they will give you. In other words, they will say this population is described by a logistic function, and then they'll give you A, B, and C. And so all that's really required is to put those things in your calculator and punch them out. So that shouldn't be too much of a problem for you. So I'm going to actually stop at that particular point and close out this video, because that gives you a pretty good idea of how exponential and logistic functions are used in actual applications. And we're done.